So the purpose of this video is to show you some of the ways that you can algebraically solve exponential and log equations. So in this first question, I want to solve for x, and so the first thing I can do, divide both sides by 3, so I get 2 to the x equals 8. And you remember that in our last video we talked about solving exponential equations by getting a common base, and you'll notice here that base of 2 and an 8, and so we know therefore that the answer is going to come out to be 3. But as we're going to see as we move forward here, that oftentimes we will not have a base in which we can get a common base between them easily, and so we will have to resort to another way. And that way is logs. Alright, here's another example of an exponential equation that's somewhat more complicated. We have a variable x in the exponent on both sides of the equation. And I'll notice that if I look at my base on my exponents, base 5 and base 2, that there's no way that I can think about changing, for example, 5 into 2 to the something. That would require a calculator, and so because getting a common base isn't straightforward, we're going to solve this entire problem with logs. Okay, one of the prime purposes of logs is to solve exponential equations. So I'm going to begin by doing the log of both sides, and now on the left I have a product of two things, and so I can break that up as the log of 3 plus the log of 5x minus 1. Remember, these are base 10 logs I'm using because eventually I'm going to have to resort to the calculator, likely. And with logs I can bring the exponents down in front because that's a property of logs. Now, to solve for x, we need to have the x's on the same side, so let's rearrange the terms here. X minus 1 log 5 minus x log 2 equals negative log 3. Lots of ways I could proceed here. I'm just going to show you one. What I'm going to do is, remembering that log 5 is just a number, I could distribute this through like so. So this would be x log 5 minus log 5 minus x log 2 equals negative log 3. My two terms with x I'm going to keep on this side, and I'm going to move this over to the other side. And at the same time as I do that, with these on the same side, I can now factor out an x. Added my log 5 to the other side. And this is a number times x, so to undo it, I do the inverse of multiplying, which is dividing. So x is negative log 3 plus log 5, all divided by log 5 minus log 2. And that is some nasty number, so I am going to use my calculator to find the value of that. It's approximately 0.56. So this is my exact value, this is my decimal approximation. So let's just roll back up and check our answer. So what I'm going to do is I'm going to plug my value of x in here to ensure that I have both sides of the equation being equal. So on my calculator, what I'm going to do is I'm just going to save this number for a moment. So I'm going to save it, so store it in one of the green variables, a. Okay, and so now when I check this, I'm going to go 3 times 5 to the exponent of alpha a, which is the stored value, minus 1. The value of the left side is this, and the value of the right side is 2 to the a. Should be the same. It is, and so I know my answer is correct. So now let's look at the solving of logarithmic equations, and again I emphasize there's lots of different ways that you can proceed with this, but I'm going to talk here about sort of two common ways. First thing I can do here is isolate the log by dividing both sides by 4 to get 3. And then one strategy for solving is just to convert the log. Once you have a log equaling a number, then you can convert that. So you have the log base a of something equaling the number. You then know that that's a to the number equals x by exponential form. So in this case, this is 2 to the exponent 3 is equal to x, so x is 8. The one thing you need to do with logarithmic equations is check, because remember that logs do have restrictions. The argument can't be negative. So when we plug our 8 back in, this is not turning out to be 0 or a negative value, so our answer should be good. The other common way to solve logarithmic equations is to set your equation up so that you have the log of something equals the log of something. In other words, you have a log on both sides. And if you can get your equation set up this way, a log equaling a log, it'll mean that those two argument pieces would have to be equal. All right? So the way I would apply that to this question is I would have to write my 3 as a log base 2. Well, I could do it like this, because I know one of the properties of logs is that log base a of a to the x is x. So if I have this 3 and I want to write it with a base 2 as a base 2 log, it's going to be this. And so what I've got set up here is the log of something equals the log of something, and therefore this something has to equal the other one. So x is equal to 8, I check it, and I see it works. So here we have a longer equation, and a couple things I look for when I'm doing log equations is, do I have the sum or difference of logs? Because I know that this is a property. If you add the logs, you can multiply their arguments. So this would be 3 times 27, in other words, log 81. And on this side, I could bring the 2 up on the x as an exponent, because that's a property of logs. And you'll notice what I've done here is I've rearranged the original equation into one of the forms I just talked about. Log of something equals log of something. So therefore x squared must be 81, and therefore x must be plus or minus 9. Okay, but I need to check. So if I put my answer back in for x, I just want to be sure that I'm not logging 0 or a negative, because we know for logs the argument must be greater than 0. So if I put 9 in there, I'm fine, but I can't put negative 9 in there. Okay, so I need to reject x equals negative 9, and therefore the solution is x equals 9. If I want to check my work graphically, I could enter 2 functions and find the x coordinate of the point of intersection, or I could set the equation to 0, and then I'm going to graph y equals this and look for the x-intercept. So let's just do that. Now in this particular question I'm dealing with base 10 logs, which is what I have on my calculator, and so I don't need to do any changing of base to enter this. It's just 2 log x minus log 3 minus log 27, graph, and I'm seeing if this graph has an x-intercept of 9. What I'll do is I'll just see, if x is 0, is y 0? If x is 9, is y 0? Yes, it is. And so that confirms my solution graphically, x equals 9. Alright, here's another equation. So the first thing I'm noticing is that I've got base 3 on all the logs. And I'm looking for that because when I'm adding my logs, I can only apply my properties of multiplying these two pieces if the base is the same. So it is. So I'm just going to jump right into that. That's log base 3 of x times x plus 4, because that's a property of logs. If you add the logs, you multiply the arguments. Equals log base 3 of 21. And you'll notice what I have. I just have happened to have fallen into the log of base 3 of something equals the log base 3 of this something. Therefore, I can drop the logs and just focus in on the solving of this equation, which is a quadratic equation. So I can set it to 0. I can factor it. If I couldn't factor, I may have to use the quadratic formula. So x is negative 7 and x is 3. These are potential solutions. I need to go back and see if these are possible. If I put negative 7 into here, negative 7 plus 4 is the log of negative 3. I can't log negative values, so I'm rejecting that. If I plug 3 in, 3 plus 4 is 7. Log of 7 can be done, not easily, but by a calculator, and log of 3 here can be done. So this should be fine. Let's check with our calculator. Now what I'm going to need to do with my calculator this time is, because I have a base of 3, I'm going to have to use the change of base law when entering this. So this would be log base 10 of x plus 4 over log base 10 of 3. That's the change of base rule, changing from base 3 to base 10, because that's what's on my calculator, plus log x over log 3. And let's bring this over to the other side to set it to 0, minus log 21 over log 3 equals 0. And so we're going to enter y equals this. Log of x plus 4 divided by log 3 plus log of x divided by log 3 minus log 21 divided by log, that was 3. I get some graph, who knows what it is. And so I'm going to check to see if the x-intercept is 3. I can use my 0 button, or since it's a nice number, just put in 3. And do I get 0 for y? I do, and therefore that confirms x equals 3 graphically. Here's another equation to solve. Now the first thing you might notice is that I have different bases, base 2 and base 3. And this may require me to use the change of base rule in solving this. But if I look at this, this is one that I can do in my head, because log base 3 of 27 is 3 to something is 27. This is just 3. So I can put that in there. And that solves the issue of different bases. Now we just have a base of 2 to deal with. And now I need to arrange my equation to get it of the form log equals log or log equals number. And I'm going to do the latter because I haven't done an example of that yet with more complex situations. So what I'm going to do is I'm going to move this over to this side and this over to this side. So I've got a constant isolated. I have 2 logs subtracted, but I can divide the arguments because that's a rule of logs. So this can be written as log base 2 of x plus 3 over x plus 5 equals 3. And so I've got my equation of the form log base 2 of something equals number. And now I can convert this to exponential form. 2 to the third is equal to the argument. That's how you convert a log to an exponent, remember. Multiply both sides by x plus 5. So this is 7x equals negative 37. Therefore x is negative 37 over 7. So x is negative 5 2/7. Potentially, but we need to go back to our equation and see if we can plug that in and it will work. So if we put in negative 5 plus 3, well, that's going to be a negative value. I can't log a negative value, so this doesn't work, and therefore we have no solution to this problem. Which should mean that if I graph the corresponding function, I should have no x-intercepts. Bring up my graph, and I'm expecting to see a graph with no x-intercepts. Final question. Now this is an equation that has logs in it as well as exponentials. And generally speaking, there is no algebraic way to do this, and so you would therefore be forced to use a calculator. So what I'm going to do is I'm going to enter this as 2 functions this time, just to do it differently. And I'm going to graph both of those. Alright, since I'm solving this graphically, I should draw a picture of what I see on my calculator screen. I should write the window dimensions below. I should mention what the functions are. And I should write a statement as to where I'm looking to get the solution. I'm looking at the point of intersection. Specifically, the x-coordinate of the point of intersection is the solution. So therefore, x equals, can't use the calculator to get my intersection. Second function, calculate. Number 5 is intersection. Curve 1, curve 2, my guess, move it close to it. And so my intersection, my x value is 1.50, rounded off.